I'm John Alukin Hodeliana, and in this video, we'll solve 3 problems related to nuclear energy. The questions are under Day 1, Physical and Chemical Principles of the Chemical Engineering Board exam. And this is specifically under the topic, Chemistry for Engineers. So for our question number 1, determine the number of days it will take for 1 milligram of rubidium-83 with a half-life of 86 days to decay to 0.6 milligrams. The choices are letter A, 132 days, letter B, 98 days, letter C, 63 days, and letter D, 211 days. To solve this problem, we can use the age equation used for nuclear decay. This is time, or age, equal to half-life, T subscript 1/2, divided by ln of 2, times ln of A0 or A0 over AT. Recall that A0 and AT are the amounts or activities of the radionuclide. We can substitute the respective amounts. The initial amount, A0 or A0, is 1 milligram, 1.0 mg, and currently at time t, 0.6 milligrams. So this is A sub t equals 0.6 milligrams. From the problem, we are given half-life of 86 days. So we can denote that as t subscript 1/2 as 86 days. Substituting into the equation, time equals half-life is 86 days divided by ln of 2 times ln of A0, 1.0 milligrams, divided by 0.6 milligrams. So milligrams will cancel, and the time or age is equal to approximately 63.379 days. So from the choices, correct answer is letter C. For the second question, determine the age in years of a mineral sample which contains 50.05 milligrams of uranium-238 and 14.05 milligrams of lead-206. The half-life for the decay process of uranium-238 to lead-206 is 4.52 times 10 to the 9 or 4.52 billion years. The choices are letter A, 2.20 billion years, letter B, 1.83 billion years, letter C, 1.30 billion years, and letter D, 2.83 billion years. We can use a similar equation to calculate this age. You're given T is equal to half-life, T 1/2, over ln of 2 times ln of A0 over AT. Currently, we have 50.05 milligrams of uranium, so we can set that as our A of T. A of T is 50.05 milligrams of uranium-238. But originally, A0 or A sub 0 contains 50.05 milligrams of uranium-238 plus the original uranium-238 that decayed into lead-206. So we are given 14.05 milligrams of lead-206, 14.05 milligrams of Av-206, and we need to scale it up to the original uranium-238. We can estimate the respective amounts using these numbers, or their mass numbers. So, from lead, we have 206 approximately AMU for lead, and for uranium-238, we have 238 AMU. So we can calculate the original amount of uranium-238. So 50.05 milligrams plus the product of 14.05 times 238 divided by 206, we can calculate A0. And A0 is approximately 66.28. milligrams of uranium-238. So we now have A naught, we now have A sub T, and we have our half-life given in the problem as 4.52 billion years. So we can substitute the values into our equation. So T is equal to half-life 4.52 times 10 to the 9 years divided by ln of 2 times ln. A naught is the previously calculated 66.28 milligrams of uranium-238 divided by the current amount 50.05 milligrams of uranium-238. Calculating, we can solve for T as approximately 1.83 billion years. So from the choices, the answer is letter B. 1.83 times 10 to the 9th power years. So for the last question, number 3, determine the daughter radionuclide when actinium-228 undergoes alpha decay. Letter A, francium-217. Letter B, francium-221. Letter C, radium-221. And letter D, radium-233. In this problem, we need to take note how to write nuclear reactions involving alpha decay. And we can also consult the periodic table to determine the atomic numbers, for example, of the actinium and the product radionuclide. So we can write our nuclear reaction, actinium, represented by the symbol AC, with the superscript 225 as the mass number. And then from the periodic table, the atomic number of actinium is 89. It undergoes nuclear decay by releasing an alpha particle, which can be represented as alpha with a mass number of 4 and atomic number 2, which is similar to that of helium. And we can write our currently unknown radionuclide X. We can denote its mass number as A and its atomic number as Z. We need to balance both the mass number and the atomic numbers. We can check for the superscripts and the subscripts. For example, 225 is equal to 4 plus A. So 225 for the balance, 225 is equal to 4 plus A. So we can have A equals 225 minus 4. Therefore, A is equal to 221. From the choices, we can eliminate choice A and choice D. So we need to check or balance the atomic numbers, which is based on the subscripts. We can write 89 is equal to 2 plus Z. So Z is equal to 89 minus 2. Z is equal to 87. From the periodic table, element number 87 is francium. So therefore, our answer is francium-221 or letter B. And that's it for our questions on nuclear energy. If you enjoyed this video, please like and subscribe. See you in our next video.